Alright, welcome back everybody. In this video we're going to introduce the concept of a parametric function, and we'll look at the first couple of examples about parametric functions, and then we'll continue next time and look at how we find derivatives of parametric functions. Basically, the definition of a parametric function: we've got x and y both defined as functions of t. T is our parameter for the curve, and so what happens is both the x and y values vary with time, and so we can create this two-dimensional representation, since we're dealing with parametric functions of x and y, and show what happens with the motion of this object as time passes. We're going to go ahead and look at example 1. We're going to graph the curve described by the given parametric equations on the coordinate plane. Then we're going to identify the initial and terminal points, and then we're going to compare this graph to one that we generate on our graphing calculator. Alright, so first of all, I'm going to let each block equal 1/2 unit here, just so that my graph is a little bit bigger on the grid. And so I'm told here that I have the parametric equations x equals 4 sine of t, y equals 5 cosine of t, with the parameter values for t ranging from 0 to 2 pi. And in order to graph this by hand, I'm just going to use my knowledge of the values of the various trigonometric functions, the sine and the cosine, at various different values, and I'm going to just plot points and see what happens. So I start when, time is 0. At time 0, x is going to be equal to 4 times the sine of 0, which is 0, and y is going to be equal to 5 times the cosine of 0. Cosine of 0 is 1, and so 5 times 1 is 5. And so the initial point on this graph is at the point, is at the point 0, 5. I forgot I was using each block as a half a unit there. So we've got the point 0, 5. And then we're going to cycle through various time values that we know the values of sine and cosine. For instance, at time pi over 6, x is going to be equal to 4 times the sine of pi over 6, which is 2. And y is going to be equal to 5 times the cosine of pi over 6, which is 5 times the square root of 3 over 2, which is about 4.330, somewhere around there. So that's the next point I'm going to plot. I'm going to go over to 2 and up to 4.330. And plot a point there. And I'll continue along that path with various values where I know both of these functions. At pi over 4, the x value is going to be 4 root 2 over 2, so 2 root 2, which is approximately 2.828. And y is going to be about 5 root 2 over 2, which is about 3.535. And so I'll plot that point. I'll go out to 2.828 and up to 3.535. And I've got a point right around there. And then I go ahead to time equals pi over 3. And there, x is going to be 4 root 3 over 2, which is 2 root 3, which is about 3.464. And y is going to be 5 times a half. That's 2.5. So we've got a point at 3.464, 2.5, right around there. And then we go down to where time is equal to pi over 2. And there the x value is going to be 4. And the y value is going to be 0. And so we'll plot that point. And now, because of the symmetry of the sine and cosine functions, I know that I can continue plotting these points, only changing the positivity and negativity of them. And so I'm just going to go ahead and plot the rest of these points by using the symmetry of the graph. Try and get pretty close here. Missed by a little bit on that one. And I continue to do that until I get to 2 pi, and at 2 pi I'm back where I started. And now I'm just going to create this curve. And so the graph of this particular parametric function should look something like that. Alright, what else was I supposed to do? I was supposed to identify the initial point. This is the initial point, right up here. It's also the terminal point. It's where it starts and where it stops. And a good idea on a graph like this is to indicate the direction of motion as time passes. And so that's what's going on, is the point is going around this curve, starting at the point 0.5 and ending back up at the point 0.5. Alright, now I'm supposed to compare this graph to one I make on my graphing calculator. In order to do that, I'm going to change modes. Down here, instead of function, I'm going to go to parametric mode. And when I do that, it lets me input the x and y functions. We've got 4 sine of t and 5 cosine of t. And then I'm going to manipulate my window a little bit here. Now notice that it gives us a whole different set of variables to enter here in our window. We've got a t-min, which is 0 here, because we're looking at time being between 0 and 2 pi. Our t-max, I've got in there, is 2 pi. The t-step is something that we can vary. The smaller it is, the longer it's going to take to graph this when my calculator graphs it, but the more accurate it's going to be. The bigger it is, the less accurate and quicker it's going to be, and I'll show you a few different t-step values. And we graph this in the window from -5 to 5, and -5 to 5. Alright, so let's use some different t-step values. I'll start with a really big one, pi over 2, and when it graphs this, I'm actually going to go back here to my y equals screen. I like to use the beaded line here so that we can see the motion that's happening. Now, watch carefully, because this is going to be pretty quick with the t value that I have. And it just jumps around. And this was a very quickly drawn graph, but not very accurate. And so we want a bigger t-step than pi over 2. Maybe I'll use pi over 30 and graph with that. And you can see the motion of this graph pretty clearly. I find that pi over 30 and pi over 60 are pretty good values. It doesn't take too long to graph it, but at the same time we get a significant amount of detail. I could use even smaller values of t, but if I did that, it's going to take me a long time to graph this. And just to take out the distortion from our screen, I'll zoom square on this, and you'll see that this looks pretty good, pretty identical to the graph that we created by hand. Alright, let's look at example 2. On your graphing calculator, graph the curve described by the equations 12 sine of t minus 3 sine of 6t, and y equals 12 cosine of t plus 3 cosine of 6t. manipulate the window dimensions until you can see a full picture. So first things first, I'm going to go in and change my functions. I've got x equals 12 sine of t minus 3 sine of 6t, and y equals 12 cosine of t plus 3 cosine of 6t. Now it says here to experiment with the window dimensions, but we can avoid experimentation a little bit if we stop and think about what's going on here. Think about the values that these functions could have. And we should be able to capture the whole picture by putting this in a window from -15 to 15 in each direction. Should be enough to catch all the values of this curve. Let's take a look at the graph. Whoa, that's pretty cool. Alright, and it just so happens that I already had, with 0 to 2 pi, I had exactly enough to get it to create this curve exactly once without the curve retracing itself. If I had used a smaller Tmax, like say from 0 to pi instead, when I made this graph, I would only get part of the graph. And if I used a bigger t value, say 4 pi, I would get this graph, but once it got done creating the graph the first time, the graph would retrace itself. And this is why I like that beaded line, because now I can see the bead retracing its steps as it goes around. It's going to be important for us when we're dealing with parametric functions to be able to come up with the interval that contains the entire graph, and also to know when the graph retraces itself. So we want to pay attention to these kinds of things as we look at, further examples down the line in this unit. Alright, that's where we're going to end this first video on parametric functions and their derivatives. We're going to come back next time and look at how we find derivatives of parametric functions and some of the implications related to those derivatives. Alright, see you then. Have a great rest of your day.